Hello, everyone. We are back with another talk at Computer Vision Talks after a very, very long break. And today we have with us Fangru. She's a PhD student, DPhil student. Is that correct? Right? Yeah, DPhil
Yeah,
student.
that's the same thing, but thank you.
Sorry.
And that's the
Sorry.
same thing, but thank you.
Yeah,
It's just
yeah,
an
I agree.
Oxford term. Mhm.
Yeah, okay. Yeah, so she's a PhD slash DPhil student at University of Oxford, and she is also presently a student researcher with Microsoft. And we came across her amazing work at ICML 2024, which is around large language models and improving efficiency within them. So I would let Fangru talk about her research after this. Thank you so much for being present with us here. Over to you.
Yeah, great. Thank you for having me. So, yeah, it's great to present our paper here. And our paper is mostly the topic is generally graph enhanced large language models in asynchronous planned reasoning. So I'll just give everyone a brief introduction first about the background. So I'll start with defining task planning. So imagine you want to make a breakfast and you want to make a coffee, make a toast, and fry an egg. Maybe the most efficient plan for you is to do all of the tasks at the same time, so you can say save time and do everything more efficiently. If you say like make a coffee, then make a toast, and then fry an egg, it will take longer. But in real life, you cannot say like do everything at the same time because you sometimes have sequential constraints. So like for example, in this task, if you want to make a coffee, you probably want to grind your coffee beans and then boil the coffee. So you have like sequential constraints in this subtasks here. So our task is basically, say, given a complicated task where you have different substeps that for which you have to sequentially execute some of them, but you can parallelize other steps. Can your large language model give you the most efficient plan for this complicated task? So our research questions are mainly three as presented here. First one is, can large language models efficiently plan for complex tasks and come up with the shortest possible time needed for them? And second, if they do not perform well, why? And the last one is, can we develop easy methods to improve their performances? And the first problem we came across is we don't have a data set. So there are some pre-existing data sets, but they're either too small or the task is not specifically defined for our task. So we decided to synthetically generate a data set to benchmark our large language models. So basically we take our base data set from WikiHow and use ChatGPT and also regex to annotate the time and step dependencies for this different tasks. So basically the base data in WikiHow doesn't have step constraints and they don't have time needed for every sub-step either. So we use large language models to synthetically generate the time for these time steps and also the ordering constraints for them. And after generating these constraints and time needed for different subtasks, we use Python to generate to parse the generated instances and generate graphs for these different instances and then compute the time needed for these tasks. So then when during inference time, we just prompt large language models with the text prompts and ask the language model to compute the shortest possible time needed for these tasks. And then we compute the ground truth, which we computed by using a symbolic processor, Python, and with the answer generated by large language model itself. And the evaluation metric is simply accuracy. So it either gets the answer completely correctly, or we think language models made a mistake. So this is the general distribution of our data set. We have 1.6K instances in total. And you can find shortest sequential path lengths and longest sequential path lengths based on the graphs we generated from here. And also V plus E is the task dependence, task complexities, which I will talk about later. And we also, the beauty of this data set is also we have a very diverse set of topics. So we have food and entertaining, education, communication, family life, and so on. So that's to say this data set is quite diverse and very close to real life scenarios. And to validate our synthetically generated data set, we compare large language model performance with previously generated a small subset of human and end-to-end annotated instances, and we find that our annotation is basically near human level performance. And also we did a very small scale human validation of a subset of the samples, and basically humans cannot tell the difference between machine generated instances and human annotated instances. So generally we think the quality is quite human level. And now we come to the benchmark models, or this is basically data generation part if there is any question.
I guess we're good to go so far. Yeah.
Okay, great. So next part is benchmarking language models. So after generating the data set, we come to benchmarking, and we evaluated 3 closed source models and 2 open source models. So we did GPT-4, GPT-3.5 Turbo, and Command full closed source models, and LLaMA-2 7TB chat and Mistral 7B Instruct v 0.2 for open source models. And the reason we use LLaMA-2 7TB chat is basically at that time, this model is somehow the SOTA level of open source models, and Mistral 7B was deemed to be a very small model, but quite good at reasoning. So we want to compare these 2 models and see if larger scale always indicates better reasoning capability. So we choose different baseline methods. The first one is zero shot, and second one is zero shot plus COT. So in case people don't know what the zero shot means here, zero shot is basically just feed the language model with the prompt with no further instruction or prompting techniques. Just ask the language model to answer the question directly. And zero shot plus COT means you use the vanilla prompt and then ask the language model to think step by step. And next baseline method is k-shot, where we essentially use k equals to 3. That means we give 3 different examples plus answers in context learning. That means proceeding the prompt you actually want to give to the language model, so that it kind of knows what the answer looks like and what the questions look like. And the last one is k-shot plus COT. That means on top of k-shot, in every answer given in different examples, we tell the language model how what is the procedure you should solve the problem. So basically, we provide a chain of thought reasoning steps in context learning examples. I'm not sure if this is clear.
Not really. What is exactly like, because some people might not be covered up with COT specifically. What is it, and why did you select it as a baseline? Is it common trend to do it for LLM
Yeah.
benchmarking?
Yeah, that's a really good question. So like I guess I forgot to mention COT is literally chain of thought. That means telling the language model to think step by step, and that essentially decomposes your task into very elementary steps. And this is a very strong baseline, and you can use it in different ways. And here we use this in zero shot and k-shot setting. And yes, COT is a very widely used method for baseline methods.
Okay, that's great. Thank you. One follow-up would be when you talk about COT chain of thought, is it an academia specific baseline, or is it like in practice in industry?
Oh, I think it's to my understanding, is in practice quite widely used as well. So basically, if you realize when you prompt ChatGPT recently, at least for some of my prompts, I don't, even if I don't tell the language model to reason step by step, ChatGPT actually answers, let's break down this task by these different ways and answer step by step. So it's actually quite inherent to language models recently.
Okay, makes sense. Thank you so much.
Thank you. Um, So,
There's another question in the chat. Can I
yeah,
pop it? Yeah. Okay.
sure.
So there's a question. Could you tell more about the prompt template or like the instruction template?
Oh, sure. So it's in the paper itself. So I don't really have like a prompt template here, but you can check the appendix of the paper.
Ah, cool. I'm
So
dropping in the link. Yeah.
yeah, great, thank you. So yeah, paper is here. Basically, you can scan this QR code and read the appendix, and it has all the details. And we also have the GitHub repo on the paper. So yeah,
Sure. I guess we can move
and
ahead.
okay, great. So like to start this task, we also developed a new method which we call plan like a graph, and we abbreviate that as PLaG here. And that is because when we think about this asynchronous planning task, we can essentially rephrase it as a graph search problem. So when we think about the making the Colzoni thing, if we say like if you look at the asynchronous part here, it looks like a graph. So you basically start we just don't have a start and end node here, but you can imagine if we have a start and end node here and connect all the steps together, it's like a graph. So when we idealize it, we find that finding the shortest possible time for this complicated asynchronous planning task is essentially the same as finding the longest sequential path on this graph. That's why we developed this method, which we call plan like a graph. And that is also why we define the complexity of tasks as a V plus E, because according to graph theory, the graph search for finding the shortest path, which is the negation of the longest path problem here, has the linear complexity. Is that good? Okay, great.
Yeah.
So yeah, so here's the more detailed illustration of our prompting template here. And I'm sorry, we don't really have baseline method template here, but you can have that and you can see that in the appendix. So this is just an illustration of our method. So compared to standard input output prompt, what we do on top of this standard input output prompt is basically adding only an instruction to tell the language model to use a graph to solve the problem. So we have two different variations of PLaG method here. One is explicit graph, which is on the right-hand side, and one is build a graph, which we abbreviate as PLaG in the middle here. So the difference is for explicit graph, we use symbolic processor to process a graph and feed that in the prompt for the model to ask the model to generate not to generate yes so like sorry to generate the answer based on the ground truth graph we give to the model. And for back here we ask the language model to generate a graph itself. So basically the only difference between back and explicit graph is whether we ask language model to generate the graph itself. Is that clear?
Yeah.
Okay, great. So, in general, this is a very simple method, and for back, it is even cooler because you don't need a symbolic processor. It's just off the shelf. You tell the language model to generate the graph itself, and then use the graph to solve the problem. And for explicit graph, you kind of need to process a bit on top of the prompt you give to the language model. But we will show later, back method actually works better for SOTA models. So this is the result we have for all the benchmarking experiments. What you can see here is our methods. Our method PLaG with two different variations beat all the baseline methods in all of the models here. So however, another interesting thing we noticed is none of the models perform well in settings without detailed task solving illustrations. So basically um for these these first three columns here, you can find that these models' performance is quite bad because in these three columns methods, we don't have task illustrations. However, in the last three columns, we do have task-specific illustrations. And we also find that GPT-4 dominates when a task illustration is supplied, and also Mistral, which is a very small model, it's only 7B, it outperforms 70B LLaMA, which means scaling does not always mean better performance in at least our task, which requires quite complicated reasoning. And another interesting thing is, so if you look at this part here, for GPT 3.5 and GPT-4, we actually find the BAG method, which is an off-the-shelf method, is even better than the explicit graph method, where we have the ground truth graph. So that means for very capable models, you can just apply our method off the shelf and expect the model to have better performance. And so if we take a closer look at GPT 3.5 and 4, which are the most capable models in our previous benchmarking experiment, we find that PLaG boosts performance across all task complexity levels for these two models. So if you remember, we defined task complexity based on graph theory, which means V plus E. And what we find here is for across all the task complexity levels, our BAG method has Pareto improvement over baseline method, which is really cool. And this basically indicates for whatever complexity your task is in, you can almost always expect our method to offer you a boost over the previous baseline methods. And to understand more about what's going on here, we want to understand what is the difficult part for asynchronous plant reasoning, because we find here that a lot of models don't perform really well. Even for the most capable models, you can see the task with task complexity increasing, the model performance drops drastically. So we want to understand what is the complicated part in these kind of tasks. So we think solving asynchronous planning problems requires three key skills: time summation, time comparison, and constraint analysis. So we compare sequential and parallel plans, which only require time summation and or time comparison with asynchronous planning. What we find here is parallel and sequential plans always have better performance over asynchronous plans on the same step numbers, which means that time summation and comparison are not very difficult for large language models, but the constraint analysis is the most difficult part. And we also understand what will happen if our tasks are even harder, because in our tasks here, so if you look at this distribution, we have very skewed data points for complexity over 20. So we want to understand if in real life you have a graph that I don't know, like has more than this complexity, what you would expect from language models. And what we did is we did a proxy by generating a synthetic data set with V plus E up to 40 for the prototypical graph shortest path search problem. And what we find here is, even given this proxy, you can also find language models' performance to drop drastically with increasing task complexity levels, which means when you have a higher task complexity, you can basically always expect your language model's performance to drop, which is not very ideal. So maybe I can pause here and see if there's any
Yeah,
question.
when you say sparse instances, what does this exactly mean?
So so basically what we find here is so for task complexity bigger or equal to 20, you only have, say, this amount of instances, and I don't really remember what is the specific number, but it's very skewed compared to other complexity levels, if that
I
makes
see.
sense.
Yeah.
Yeah.
There are multiple questions. So the first
Mhm.
one comes from Arbaz. Also for the audience, if you prefer to have a discussion and your question is not answered, please feel free to ask us to unmute you. So the first one is, can you explain the graphs on slide 13? What's the difference between the two graphs? So, yeah.
Oh, I see. So the first figure on the topmost figure is the figure for all baseline methods. So what you can see here is basically these methods are methods without task illustrations, and this method is the best performing method is K-shot plus COT, and this line is for GPT-4, and this is basically the best performing method for all the baseline methods. And then we move to this part here. We only compare the best baseline method with our best performing method in this figure on the bottom side. So what we find is our method offers a Pareto improvement over the best performing baseline method across all task complexities. But what you can find in common in these two figures here is you always find a different prompting method to have decreasing performance with increasing task complexities, if that makes sense.
To me, yes. Arbaz, if your question is not answered, please feel free to follow up. There's another question from Eman. I'm curious to know what happens if one of the subtasks fails.
That is a very good question. So I think that's beyond the scope of our paper, but I would think this is a very interesting direction to follow. So basically, instead of having this kind of static graph, if you have ones that fail, you probably want to update your graph, and that will give you a dynamic graph planning problem. And this is something we haven't explored yet in our paper. So if you're interested, this might be a really interesting follow-up.
Sure. Thank you. So yeah, that answers both the questions, and we can proceed.
Okay, great. So we're also interested in what will happen if we use trivially different prompts, because it's widely known that large language models are not very robust to different forms of prompts, even if they're just trivially different and have the same intentions. And so what we do here is we vary different graph types and we vary different prompts. So for example, we have 4 different graph types to represent the step dependencies. We have edge list, adjacency matrix, compressed sparse row, and adjacency list. And for different prompts, we mean something like we use different forms to represent the step dependencies. So instead of saying step 1 must precede step 2, we can also say step 2 must follow step 1. So what we find here is varying these graphs in trivially different ways, either varying graphs or varying text prompts. You always have a performance say like a gap between the best performing prompt type and the worst performing prompt type, which means your language model is not very robust to different kinds of prompts. And another thing is we find that for different models, they prefer different kinds of prompts. So like, for example, for GPT-4, we find edgeless to be the most preferred graph type for it. But for other models, so like, for example, Mistral 70B, excuse me, Mistral 7B instruct, compressed sparse row is the best performing graph type. So you kind of maybe kind of want to do some preliminary experiment by using a small batch and prompt your language model to kind of get an intuition about what kind of prompting type is the best performing one for your language model. And we also further varied text prompts in the extent that we can combine different prompts together. So instead of saying something in detail, like step 1 must proceed step 2 and step 1 must proceed step 3, humans can also say something like step 1 must proceed step 2 and 3, which is a more economic expression. And what we find is even by using this economic expressions, your language model can also experience a performance drop. And this is quite interesting. So that means language models are not really robust to trivially different prompts. So any questions?
No, none right now.
Okay, great. So basically the main takeaways here in this paper is are first, PLaG can consistently boost model performance across all complex planning tasks. And second, on top of general prompting techniques, it is probably useful to rephrase your problems in a way that language models are familiar with. So if you think about our graph representation, it's basically nothing more than just use a different form to represent the step dependencies and time needed for different steps. But it seems that language models can just use different forms of the same prompt with same intentions to solve problems more easily. And that is probably because language models are more familiar with the graph search problem itself. And the third is large language models are not robust enough to be deployed as digital devices. By this, we mean that since for digital devices, if you have an Oracle model, you would expect your language model to always have Oracle performance, which means accuracy of for 1 across all the task complexities. But what we actually observe is that your large language model's performance actually drops a lot with increasing task complexities, which means that they're not robust enough to be deployed yet as digital devices. So here are also some like possible future directions that I've been thinking about. So first, we find rephrasing planning problems in a graphical way is helpful. So is there a method to rephrase problems in other settings, or can graphical prompting also help solve other problems? And second, in this paper, we take a quite naive assumption that infinite resources are available. So for example, we have infinite agents and tools, and also we assume that as someone mentioned before, we don't really assume that you can fail at some steps. And so we don't really know how will our language models performance to change with finite resource settings, or when we have, say, like steps where language models can really fail. And the third one is graph search works a lot better than a novel natural tasks in language models. How can we attribute this prompting success to memorization? So like, oh, I mean, here is basically, so our task is very new. We generate a new task ourselves so we can make sure that language models have not seen this data set before, but we don't really know if these language models are trained on graph search, so they're familiar with this problem, and we don't really know if that's why when we prompt model in the graphical search way, they can perform better. So we want to understand how we can attribute this success to memorization if we can. And that's basically all. And you can scan this QR code to see our paper and also follow me at basically everywhere. So thank you.
Awesome. That was a great presentation. We have two questions in the chat box. So the first one is, can you please explain what the economic expressions are?
Oh yeah, so that's a really good question. I guess I didn't get this super straightforwardly. What I mean by economic is, so in linguistics, If you have say a shorter sequence, we call that a more economic expression. So according to pragmatic theory, what you can expect is you can be as a rational speaker is expected to be as succinct as possible, and as long as the speaker can express the speaker's intention sufficiently. So this is a quite natural expression to say step one must proceed step two and three, instead of saying step one must proceed step two, step one must proceed step three. It just means a shorter sequence, but like say like a compressed way, but expressing the same meaning.
Okay. Okay, that's understood. There's another question, which is, have you compared any particular instance where the proposed PLaG model fails versus where the K-shot plus chain of thought method fails? Are the modes of failure similar?
That's a very good question. So we didn't do that experiment. As long as I remember. No, but we did try to find like why in some of the easy cases language models fail, and why in some hard cases language models succeed. So basically what we find quite interesting is like some of the models cannot even calculate time correctly, even when it guess how to what kind of steps to select to calculate the time in these different steps.
So I think that would be another thing to explore. Eman, you want to unmute yourself? You can do that.
Yeah, I had a quick question. So it is very interesting approach, and I feel like it's very efficient. I wonder if you executed the steps, or it's more about the planning and the different approaches of the planning. Like, was there an environment, for example, some embodied AI environment where you executed and started to get feedback from the agent, or it's focusing more on the planning part?
Yeah, that's also a very good question. So this paper is only about planning. So we only design the plan instead of executing the plan itself. But I think that is also a very interesting direction to explore if you're interested. So basically, I mean, not all of the plans are optimal. If you have finite resources, your problem can be NP hard. So it's basically impossible to find the optimal solution. But what you can do is when you can design a plan and get feedback from the environment and to refine your plan.
Mhm.
So
Yeah.
yeah, and also yeah, like when you fail, you also have to redesign your plan.
Yeah, yeah, that's very interesting. I will definitely follow up later. Thank you.
Thank you for your question.
Awesome. So are you continuing to explore the same direction for LLMs, or are you changing the project? It's off the paper.
Uh, like yeah, that's definitely an interesting question, and I get kind of asked about this all the time. So like I can generally I generally want to switch a different direction when I finish one project, but I'll definitely come back to this paper because I think it's still quite interesting. I mean, the most interesting part for me in this paper is not like how the method boosts model performance, but it's more about well how like you can just rephrase something to get a better performance. And I kind of want to understand why and how can we make that robustly generalized to other different tasks. I mean, in this paper, we only explored planning, but I was also told that our method can like some of my colleagues are also using this method in tasks like long text generation. So I think it would be really cool if we can see if this kind of intuition can apply in other tasks as well.
Mhm. I have two more general questions. But if from the audience someone has more doubts on the paper, feel free to drop in the chat, or if you have general questions like me. Uh, so it's your choice to answer them again. So the first one is that how computationally expensive all of this research is now, like hosting these models, what kind of machines are required? How are we progressing?
Oh, that's also a very good question. So like that's very practical. So So for the closed source models, they are API based, and we basically apply for credits to run these models. And for open source models, we actually also run we in practice also run the big model on API, and I think we run a small model on GPU.
Mhm.
So like for GPU, I think you can run 7B model. Actually, I don't really remember if we run that on GPU or something. But like I'm pretty sure you can run the smallest 7B model on one single A100. Yep.
Okay, sure. Yep. You can unmute yourself, Raymond.
Okay, yeah, sorry to ask again.
Mm.
I wonder if the number of tasks you're trying to plan like concurrently is the number tunable. Like for example, are you for example trying to solve 3 tasks at a time or 5? Is there like n certain number that you are trying to tune, or it doesn't matter at this point?
Uh, I don't particularly follow. Can you repeat?
Yeah. So at the very first, when we had like
Mm,
prepare breakfast, make
mm,
coffee, and another third task. These were 3 tasks
mm,
that we saw at the very beginning of the slides.
mm.
So the number always 3 in the experiments, or did you change the number of tasks?
Oh, you mean this one?
Yeah, and then I was meaning the one, yeah, this one, like these are 3 different tasks.
Mm, mm.
Um, So is the experiments about always having 3 tasks so the graph is always
Oh, I see. No. So like, oh, we have different tasks. So like this is just a toy example, but
okay?
this is a real example in the data set.
Oh, okay. Oh, so mainly focusing
Yeah,
on the medical zone. Uh,
yeah,
okay, I see.
yeah. Like basically the tasks are like how can I make calzones, and it's like cooking and entertainment, and how can I reach the closest amusement park or something.
I
So
see.
we have, yeah, like all of the data points are from WikiHow. So I'm not sure if you're familiar with WikiHow. It's basically like a website that tells you how to accomplish your tasks. So it's always human written, and they have different steps and different tasks.
Okay, so you are trying to parallelize subtasks of one big task.
Yep.
Okay, I see. Awesome, thanks.
Interesting.
All right.
Thanks for your valuable questions, Raymond. Um, okay.
Oh yeah,
So
so I found sorry to follow up on your hosting device problem. So we actually used um one A100 GPU for Mistral 7B instruct inference, and for other time we also we also tried to use 2 V100 GPUs, and that
yeah,
also worked.
yeah, I guess Llama needs 800 as well, or 4090.
Yeah.
Mm,
Yeah,
Okay,
you can run like multiple V100, and that should also work.
awesome. I'll have one last question from my end, and that will give audience time to remember if they've missed any question. And I'm sure they can follow up with you afterwards on your social media profiles. You can put the QR on the screen.
Yeah.
Okay. So the last question from my end is again generic because I have more of a computer vision background. Are in NLP specifically, are we moving towards evaluative research rather than a generative one? Because like we already have so many LLMs being updated and they are being updated at an industry shark level. So is the research from academia moving more towards evaluation of how they are behaving? Because the recent works that I have been reading are more towards evaluating them.
Yeah, that's also a very good question. So I think mainly there are 2 reasons why probably there are so many like evaluative works searching, and one is like generally academia is quite um GPU resources are quite expensive, and it's quite difficult to train a lot of language models. And second is probably, at least for me, I want to understand what's going on. And like there are different groups of people. Some people are interested in making things work, and some people are more interested in understanding why things work. And I guess evaluation is in the vein of like understanding why things work. And I'm also interested in like combining a little bit of both. So basically we know language models are very capable, and we want to understand what are their limitations. So that means we always want to evaluate them. And generally, when we think language models are more capable, we want to test them on more tasks. And that is why we have more benchmarking papers. And also just after testing their capabilities, we can develop some method to improve their performance or just see what's going on.
Of course, yeah, makes sense. If everyone starts building, we would never know which one is the best.
Yeah.
There's another question, okay, in the chat. Was any accuracy comparison for tasks with more branches versus less? Okay. Did you compare accuracy for this?
Yeah. More branches versus less. Okay, so this is basically, I'm not sure if this is what you mean, because V plus is literally vertices plus edges, and maybe that's quite similar to branches that you mentioned. So this is basically task complexity, and yes, we see a decrease of task performance here.
I see. I hope that answers your question, Dan. Okay. So this was it from my end, and I guess from chat as well. Yeah. Okay. Perfect. Okay. There are thank yous for you, Lynn. Awesome. Okay, perfect. Thank you to the audience for sticking with us till the end. And yeah, thank you so much, Lynn. This was a very good talk. I'm sure I'm going to find interesting papers, and we look forward to what research you follow up after this. Thank you for agreeing to have a talk with us.
Thank you so much. Thank you for having me.
Great. Awesome. See you soon. For everyone else, the audience, thanks again.
Yeah, thank you. Bye-bye.
Bye-bye.